Hello everyone, today I will show you how to do a particle flow simulation using EDEM software. EDEM software is uh, used for DEM type of simulations, and DEM means Discrete Element Model, and it is used for particle simulations, particle analysis. So here is my geometry here, and this is the case of the helix. And let us hide this, and this is our helix, which will be used for transportation of particles from one end to another. And uh, as you can imagine, this is the inlet and this is the outlet. So let us go to the EDEM software. So this is the main page of the EDEM. As you open it, you will encounter this screen, this interface, and I am using EDEM 2017 version, and I don't know if there are differences throughout versions or not because I didn't use any other version, but I think there won't be so much differences between versions. So let us first define a title for the project, and which will be tutorial, transportation tutorial. And as you can see in the creator tree, the program actually shows you how to take your step forward in your simulation, because uh, it there are everything you need to define your model. So I will first define a bulk material, and this bulk material will be the material of the particles. So this is my bulk material properties, and I will not change them because I do not have any real model to simulate. I am only uh, doing this analysis for this tutorial. So I defined my bulk material, and let us call it particle material. And if you right click on the your material, you can see there is add particle selection, and let us click on it, and you'll see we have our particle interface here. And uh, as most important thing is the defining the shape of your particle, and I will have a single surface, a simple sphere particle in this tutorial, and it is radius will be 10 millimeters, and that is all. And also you must click on calculate properties here, because if you do not, it will take the mass or volume as 0. So you must calculate these properties. As you can see, it is all defined now. So I will add an equipment material, and this will be the material of your geometry, your case actually. And let us call it geometry material. And also I will not change them. So I need to define some, oh, sorry, let us rename this also as particle. So I need to define some interactions between particle to particle and geometry to particle. So I will click on this plus symbol here and select particle material, and this will be the interaction between uh, particle and geometry. And if I go back to the particle material, I will define one more interaction, which will be particle to particle interactions. And I will not change the coefficients, but you can change if you want. You can change friction or rolling friction coefficients or restitution coefficients if you want, but I will not change them now. So I have defined my materials and my particle. So I will import my geometry from this geometry tab here and right click on it, import geometry, and I will select helix geometry here. So this is so important because you must choose the right unit of your geometry. It will defaultly come with meters, but it will not in this case actually, because this geometry here is drawn by millimeter dimensions, so I need to change it to millimeters. So this is the geometry import parameters here. I will not change them. This is okay, and I do not recommend you to change them. So it is importing the geometry. So yes, geometry is imported, and as you can see, here is our geometry. And as you can notice, the geometry comes, the geometry came with many parts. This is actually a good thing because we will define some rotation to the helix, and we will define inlets, outlets. So we need some separate parts to define these features to the geometries. So let me find the helix geometry here, and that is it. This geometry is our helix, and I will right click on it and say add kinematic, and I will add a linear rotation. So okay, and I will change the velocity to 100 rpm. And so you need to define an axis of rotation, and this is a bit this have a bit some troubles because I do not know the origin now, and I need 2 points on my shaft which is carrying the helix. So I will go for the shaft geometry. Let me find, and here, and I will click on mass, and as you can see there is my center of mass of my shaft, and which is the middle point of it, and I will copy this middle point's coordinates to my starting point for my axis of rotation, and let me copy them. So I have now 1 point and I need the second point. So for this I can use these plugs in the both ends. So let me find one of it, and this is one plug on the right end. So I will take its mass center, and its mass center will be on also along the shaft because they are all circular parts, and I will define it as endpoint of my axis of rotation. Here I defined my axis of rotation, and if I click on display vector, you can see this is my axis of rotation. So let us check the rotation orientation. So it is in the in the wrong orientation, because in this orientation the particles will flow left to right, and we want particles to uh, move right to left. So I will have a minus sign before my angular velocity term. So okay, my kinematic and my rotation is defined, and let us rename it as rotation. So okay, so next thing is I need to define my inlet. So to define my inlet, it is a bit problematic because as you can see, my inlet is here, but my this geometry is empty. It is a hole actually, so I cannot select this surface because it is empty. So I need to define a surface in here and define it as inlet. So I right click on geometries and I say add geometry, polygon, and I will go for the polygon section. The number of edges will be 32 because 32 edges means it is a circle. So I will change the orientation of the surface because it must be parallel to this geometry. So I will have 0, 1, 0. So this is my radius. I will change it to 100 millimeters. So, and the next thing is I need to locate the center of the circle. For this, I can use this geometry's center of mass because it will be the same coordinate for the circle center. So let me find this geometry, and which is here, and I will take its mass center and I will copy it here. So yes, as you can see, the inlet surface is well fitted to my geometry and it is in the right orientation. So one thing you must do is you must change the type of the surface to virtual, because in EDEM, if you want to add factory to one surface, it must be virtual. So I right click on add factory, and as you can see, this is my particle generation interface in EDEM, and I will change the generation rate, which is particle generation per second, to 500, and I will have the total number of particles as 5000. So my factory is defined, but sorry, one thing left to do, which is I need to define an initial velocity to particles, because I want particles to go in the geometry, not stay here or go in another direction. So I will have an initial velocity of -2 meters per second in y direction. So okay, my factory is defined, and let us call it just factory, and I will go for physics. So it is correct. This no-slip model is okay for particle transportation, and I will go for the environment, and I need to change my gravity because, as you can see, as default it is in Z direction, but I need to have it in Y direction. So I will have 0 here and have 9.81 here. So okay, my model is ready. You can change these interaction coefficients because they are very important actually. I didn't change it, but if you want a real like simulation which is close to the real reality, you need to change those coefficients, but I will not change it this time. So yes, I will go for the simulation tab, simulator tab. For this, you need to save the file, which will be transportation tutorial. So this is my simulation interface. From here, uh, we will change some things for the analysis. First of all, I will change the simulation time to 10 seconds, and I will change my cell size. Cell size is very important actually. It can be taught as meshes of analysis. So if you click on this estimate cell size option here, you will have the best cell size calculated from by the program. So it says 3 radius is okay for this simulation. So I will have 3 here, and I will change the time step because with this time step it will take so much time to solve this analysis. I will increase it, not this much of course. Let us see 20%. If it's 20%, we have this much of iterations. If it is 30, I think 40 is enough, or maybe 60 we can say. Yes, 60 is enough. And I will change the number of CPU cores which will be used for the simulation to 6, because if I select 8, it will use all of my processor capacity and I cannot do anything else uh, during the simulation. So I will click on this play button and it will start the simulation, as you can see. And during the solving process, you can see actually the motion of particles as it doing the simulation. If you click on the auto update, you will see the real-time uh, solutions. And if I select the display mode as mesh, as you can see, I have my solution process here, and particles going in, and everything is seeming fine. So I will stop the video here and uh, come back when it is completely solved. And yes, I'm back and the model is solved. As you can see, the message. So yes, from here we can see the particle orientations at different times by using this option. And this simulation took around 10 or 15 minutes to solve, and you can increase or decrease this solving time by controlling this time step if you want. And let us go to the post-processing section, analyst, and let us change the display. First, let us find which is the case, which geometry is the case, and I think this geometry is the case, and I will have it meshed. I will display it as meshed, and now I can see the particles here. And let us restart the video, the particle video, and as you can see, I can see the particles moving around the helix. You can you can export this video from this selection if you want. So let us do some post-processing things from here, and let us color the particles using some features. Let us say uh, coloring by compressive force, for example. And as you can see, you can change the colors if you want. You can change the values uh, which color take. And let us define a maximum value, which will be 25 newtons of compressive force. As you can see, you can trace the compressed particles here, or we can have the coloring by velocity, and which will be this value. You can use this option to have an average velocity value to color by. You can see the values, the particles are colored by their velocities. And also you can create some graphs easily using EDEM. And let us say we want to have line graph, and the x-axis of the graph will be the time, and y-axis will be, for example, the torque generated by particles. And let us have the average torque, and from the bottom you can click on the create graph option, and as you can see it is generating the graph. It will take some time, but not so much. So as you can see, we have our torque graph here. By the way, using the average torque so is not so actually compensative, because uh, on each part of the helix there are different torques, and you cannot uh, decide on which part is critical or not by using this graph, because it is averaging the whole length of the helix over time. So I think using total is much more will be much more uh, good for this simulation type, because we had so small values of torque. It is generating the graph, and as you can see, we had some more logical torque values now. Also, you can change it to maximum if you want to find critical times of the transportation, or we can uh, create a graph of another feature, for example, compressive force. Uh, in this, if you select the group as particle, it will create the graph by torques on the particles. But if you want to find the torque on the helix, you need to change the geometry there. Let us find our helix geometry. It is imported one. So uh, let us select our group as geometry and our section as imported one, and it will give the compressive force on the helix now. So I will click on create graph. So yes, as you can see, we have our compressive force graph here, and from this graph you can decide on which time it is critical uh, in terms of compressive forces. For example, here the 8.2 seconds is much more crucial than other times. So this is it actually. The post-processing of EDEM software is very user-friendly. You can, if you wander around the interface, you can easily learn how to post-process your simulations. And one more thing I want to show you is If you want to change something in your simulation after you solved it, if you just, for example, go to creator part and, for example, change some features. For example, let us define our radius is 15 now. If you just change it now and go back to the simulator, you will see if you run the simulation again, it will solve in no time, because actually you did not change your properties now. If you want to change something, you must go, for example, let us uh, call it 10 millimeters of radius again, and if you want to change it, you must click on this button here to take it back to the 0th second, and now select 15 millimeters of radius, and now go to the simulation tab, and now as you can see it is saying uh, all solved time steps will be deleted, and if you run again, it will actually solve the simulation again, and you will have it changed now. I had some trouble about this while learning EDEM, and I wanted to show you this. So yes, I think this is enough for this software. I am planning to record one more tutorial about EDEM, about handling particles on a bucket, dropping them off for loading. I want to show this also, but I don't know when I will record the video. But EDEM is actually so much user-friendly software. I think if you want to do another thing, another type of simulation in EDEM, if you wander around the program, you'll see it. It is so easy to control the simulation, and I think that you will not encounter any hardness in this program. So thank you for watching this video, and see you later.